In this question from CSIR NET December 2024, we have a system consisting of n distinguishable atoms, and there are two energy levels, one with energy omega, the other with energy 3 omega. We have to calculate the upper limit of average energy per particle for this system in thermal equilibrium. Average energy, this is equal to summation over n En Pn, where Pn is the probability of occupying nth state in thermal equilibrium, which is given by e raised to minus beta En divided by Z1. Z1 is the single particle partition function. Because we are only needed average energy per particle, we have to use only single particle partition function. If we need total average energy, we use n particle partition function, which is Z is equal to Z1 the whole raised to n. This can be used when system is distinguishable, but here we are not needing that because we only need average energy per particle. Another formula for average energy is equal to minus del by del beta ln of Z1. This is average energy per particle. Let's use this formula because I have already solved problems using the first formula. Let's use the second formula here. So average energy per particle, in the question it is denoted by epsilon EQ. This is equal to minus del by del beta ln of Z1. Z1 is partition function, which is single particle partition function, summation over r e raised to minus beta ER. Here there are two states, so we have two terms in summation, e raised to minus beta omega plus e raised to minus beta 3 omega. Therefore, epsilon EQ, average energy per particle, becomes minus del by del beta of ln of e raised to minus beta omega plus e raised to minus beta 3 omega. So epsilon EQ is equal to minus of 1 by e raised to minus beta omega plus e raised to minus 3 beta omega. Now you take the derivative of this thing, which is minus omega e raised to minus beta omega plus minus 3 omega e raised to minus 3 beta omega. Therefore this is equal to omega e raised to minus beta omega plus 3 omega e raised to minus 3 beta omega divided by e raised to minus beta omega plus e raised to minus 3 beta omega. If you divide all the terms by e raised to minus beta omega, this will be equal to omega plus 3 omega e raised to minus 2 beta omega divided by 1 plus e raised to minus 2 beta omega. So we are dividing numerator and denominator by e raised to minus beta omega, and then we are getting this. Now there are two cases. To get the lower limit of energy, we can use T tends to 0. All particles occupy ground state when temperature tends to 0, and when T tends to infinity, we get the upper limit. When temperature is tending to infinity, probability of occupying different states become equal. So probability of occupying the highest energy state and the probability of occupying the lowest energy state all become equal. Therefore, to get upper limit, we have to use T tends to infinity. So when T tends to infinity, beta is equal to 1 by kT will tend to 0. Therefore, when beta tends to 0, e raised to minus 2 beta omega, this will tend to 1, and this also tends to 1. Therefore, we have epsilon equilibrium is equal to omega plus 3 omega times 1 divided by 1 plus 1. So when beta is tending to 0, we have e raised to minus 2 beta omega equal to 1 by e raised to 2 beta omega is tending to 1. That's why we have epsilon EQ is equal to omega plus 3 omega divided by 2, which is equal to 2 omega. So this is the upper limit of average energy per particle. Therefore, the correct option here is option 4. Thank you for watching. If you found this video helpful, consider subscribing this channel if you haven't done that already. Thank you.